All right. Glad to see everybody here. I know we have a few more attendees rolling in, so we'll just give everyone a couple minutes to sort of get on to the meeting here. I want to welcome everybody in to our kickoff meeting for the season. Hopefully everybody's got their lunch and libations ready to rock here on the other side. We had about 70 register for this. Hopefully the registration links didn't get filtered too much into the junk emails or folders in people's systems. We seem to be having issues with that lately. Probably a sign of the times, sort of as the saying goes. All right, people can filter in a little bit later. I want to thank everybody for being on today. As you know, this is our virtual meeting for the month. Preservation and repair of existing concrete structures. We're excited to have everybody here. The board is all with us today here. I'd like to thank all of our board members for what they do. Obviously, they're volunteers in this, so I want to thank everybody for volunteering. I also want to take this chance to introduce our new board members, Nathan and Justin. Thank you guys for jumping on the board. I don't know if you guys want to real quick do an introduction. I know, Justin, you're here. Why don't you say hi to everybody?
Sure. Yeah. Hey, welcome, guys. My name's Justin. I'm currently work for McCormick Taylor as a structural designer, and I've been working there for about almost a year and a half, 2 years now. Yeah, I'm just glad to be on the board and to help out any ways that I can.
Glad to have you. Nathan, why don't you pop in too?
Sure. Good afternoon, everyone. Nathan Dubbs with BDI. Happy to be on the board. Looking forward to participating and being a member here for the next few years. I work at BDI. I've run our office in Horsham for the past 6.5 years now, um, specializing in instrumentation monitoring, NDT, and all those sorts of fun aspects of our engineering world. So thank you.
Thank you, Nathan. We're happy to have you. Um, I don't know if anybody else wants to chime in, but go ahead and do as you'd like. Um, we definitely want to thank our sponsors from the golf outing last year. Hopefully, this slide will advance. There we go. And definitely put a save the date in for the next one. We're tentatively going to have it on the 9th of May out in Kimberton. Happy to see everybody come out again. And once again, I want to thank all the sponsors, AECOM, HNTB, GM's Controls, Pickering Court, Scanit, SAI, Panoni, for sponsoring the golf outing. This golf outing is really the primary way that we can sponsor the scholarships for up-and-coming structural engineers. You know, as engineers in general, we want to keep the students interested and help them out as much as we can in terms of getting their education and getting involved in the industry. So feel free to certainly join us. We're going to have information coming out on that likely before the end of the year, so people can start registering and getting on board. And if you do sponsor, we're happy to have you on our slides for these events and in the in-person events. So just so everyone knows, and to be totally clear, this event is being recorded and it will be available online through YouTube and our website in terms of future needs and reviewing. Your microphone, if you're attending, and camera have been disabled. Please use the messaging or chat function if you do want to participate in general. We'll certainly be checking that as we go through. However, if you have a question that needs to be answered, please use the Q&A function to put questions in. For this presentation, our intent is to do the Q&A at the end. So certainly please hang around. And what we will do with the certificates is I'm going to have two things. I'll have a QR code you can scan. So if you want to take a screenshot of that or you have your phone handy, you can do that. And then at the end, I will put a link into the chat for you to get your certificate. Certainly, we want you to stay up to date on events and get involved as much as possible. So you can use our website. Websites, I guess, are getting a bit old. Certainly, feel free to email us. We're constantly checking email. And the QR code you see on the screen here is actually for LinkedIn, for our chapter site. My expectation is LinkedIn will probably become more and more the place for us to do real-time updates on events and other things going on in the Philadelphia chapter. So we do look forward to everybody getting involved moving forward. And speaking of events, here's some upcoming events that we do have and dates. We'll be sending out emails for those and so forth. Also, we'll be linking those on the LinkedIn site for easy registration, hopefully. We are looking to do Winter Social, and we have a great panel for students coming up in February. And we would ask that some of our structural engineering colleagues volunteer. Let us know if you're interested to be on the panel for the students at Swarthmore College. That's great for them in terms of them closing out school and getting a good handle on what it's going to be like to be in the industry. So without further ado, I would like to introduce today's speaker, Keith Kesner. 25 years of professional experience, so he's been doing this a long time. Certainly asked some questions and learned some stuff from him. Concrete, we all deal with concrete in our lives, and concrete doesn't last forever, I guess, unless you're a Roman, which they seem to have figured it out, and we forgot all about it. BS from Connecticut, MS, PhD from Cornell University, so right up there with the smartest of the smart. So I am so happy to be in your presence today, sir, and I look forward to you getting rolling here on the slideshow.
All right. Thanks, Nathan. I'm going to start sharing my screen, and let's see if I can get this to work properly. There we go. I think that's correct.
Looks correct to me.
All right. So I'd like to thank everybody for coming today. Thank you for Nathan and Keith for the invitation. Thank you to the board. And it's really nice, as Keith mentioned in the intro, I'm a active member with ACI. I've done a lot of stuff with various ACI committees, and it's nice to be able to the opportunity to talk to an ASE, SEI chapter. I don't think it's something that we do enough. We tend to get siloed with professional organizations, and granted, nobody has enough time, but it's nice to talk to different people about different things. And the topic today is something that's extremely broad as a topic. Evaluation and repair of existing concrete structures. That's huge. And this is really a presentation that's going to talk about some new documents that have been developed by ACI, trying to tie them in with some code, with some examples, some case studies as to how they're used, and hopefully start maybe just a conversation. And if anybody has questions, I'm happy to follow up with them. And you put those in the chats, we'll get any questions that you have answered. And I always forget. Oh, I always forget how to advance slides for some reason. You do enough. Every time I do it, it seems like it's someplace different. But all right, here we go. So a lot of this presentation is warranted, as Keith started at the intro. Concrete structures don't last forever. Steel structures don't last forever. Masonry structures don't last forever. And then repaired structures are sort of a different animal. And a lot of this presentation was based upon, 30 something years of experience with repaired structures and how we're dealing with them. And if you look at the graph, the kind of Jamaican flag graph that my friend Nam Shu and Kyle Stanish originally put together, you always want to keep our structures in the green zone. And to do that, to keep them in the green zone, we do maintenance, we do repairs. The question is, how durable and how long lasting are those repaired structures? We're going to talk a little bit about some options for repair design, different materials, and some of the background testing as to how we assess it. And as I said, this is a hugely broad topic, so I'm really just scratching the surface on a lot of these topics. But I always loved, just thinking about existing structures, I always loved this quote, and I had to do a little bit of research to find out where it originally came from. And you can see the reference down there. It's by a gentleman named Dr. A.R. Dykes. And we're talking about, it's obviously a British spelling, but we're talking about molding materials we don't understand into shapes we can't analyze to withstand forces we don't really know about in such a way that the public has no idea of how stupid we are. It's basically what he said. And when we start to think about existing structures, that's new structures, that's brand new structures. We start to think about existing structures, you have that. Now you throw them out and you leave them out in the wood, leave them out in the environment for 100, maybe 100 plus years. You don't maintain them. And we don't really understand degradation. Most design professionals really don't understand degradation of existing structures. So what are the problems? What do we end up with? This problem of repair performance been studied both by the Corps of Engineers in the United States and in the UK by the British Research Establishment. And they produced the graph that's shown in the upper right. This is the British Research Establishment's graph. The Corps of Engineers data is very similar. And it basically says, once we start repairing a concrete structure, repairs do not last. Most repairs are failing in 6 to 10 years. And that's kind of disappointing because we all know what the problems are once we start to have to repair a structure. And in the pictures, you can see some failed repairs. Why is this happening? We don't really practice durability design. It's not a common design. It's not a common design condition that we're actually thinking about. In the last 10 years, Federal Highway said, okay, now bridges are going to last 100 years. They did that, and we really, this is my opinion only, and other people can disagree with me. In my opinion, despite that mandate, we really don't have great consensus on how to do that and how to achieve a specific service life. And in my opinion, also, the US practice is a little bit behind international practice. There's some much better practice in Europe and Australia for durability design. And that really, in the US, it's really an origin is that we don't understand existing structures. And that's because we're not learning about durability as undergraduates or grad students. The result of this is really there's questions about safety of existing structures. We all hear about chunks of buildings falling off of facades. At least in Philadelphia, if anybody operates a parking structure, I'm not talking about your parking structure, but most of the time I go into a parking structure. Some of my questions are, is something going to fall on my car, or should I park on the sidewalk and risk getting carjacked? And that's kind of a sad commentary. So why is this happening? Really, we're not understanding the root cause of the problems. We don't do sufficient evaluations, and we're not detailing our repairs. So what does this look like? So a couple pictures from failed repairs. These are from my friend Tarek Al-Qardaji, who works at Structural as a repair contractor. And these are all different structures that have had multiple cycles of repair, as you can see in the sort of the cool looking mosaic on the left, or more ugly looking things where there's massive cracking from improper repair design, or combinations of corrosion damage plus repair failures. You can see over here, you can see these are actually FRP strips that failed prior to this big section falling down. That's kind of some of the things, and these are just in parking structures. We can also have similar things in bridges or other types of structures. So why are we getting these premature repair failures? Really, it starts with concrete design, the problems with concrete design. In essence, building codes, whether it's for a building or a bridge, they allow us to build it's the least safe structure that we're legally allowed to build, because a code provides a minimum requirement. Anything less than a minimum has been deemed to be unsafe. We can always do better. We can always exceed the code requirements, but the codes are always telling us that it's going to have the least durable or the least strong structure we can build. And entirely, in my opinion, our education in civil engineering and structures, it's entirely focused on structural behavior. We really don't have a lot of coursework on durability. And we look at the building code, but this is predominantly talking about ACI 318, it lacks an integrated approach to durability. What do I mean by that? Durability in concrete structures is really a question of keeping water and other deleterious materials out and making sure that the materials that you have are going to be durable. And that includes both the concrete and the reinforcing steel. If you will read through the ACI 318 code and commentary, you'll never see that discussed. They talk about minimum requirements for concrete for initial structures based upon exposure. They'll talk about different types of reinforcing steel. You can use epoxy coated, you can use galvanized, you can use regular steel. But there's really never a discussion about how you can put those together to create a more durable structure. And what's the end thing that happens? We're not achieving our service lives. We have this cycle of repairs. And the cycle of repairs really is a problem for us as an industry, because it makes us look, I mean, honestly, it just makes us look bad. We drive through structures, we see them falling down. I drive on 276 all the time. There's one bridge as I'm heading towards New Jersey. There's been a chunk of concrete fell a couple of years ago at the intersection of the girder with the parapet. A bigger chunk fell recently. And if I wasn't so lazy, I'd pull off the side of the road, take pictures of it, but I'm a little bit nervous about doing that. But it's, you look up at some of these things and you say, yeah, this is a problem. And what are the engineers doing? So how can we focus on that? How can we do better? We need to, for design professionals, to start thinking about repair as a distinct area, understanding better how we can evaluate durability and evaluate structures. We need to get contractors focused on qualities and really need to start changing US national codes to produce a more holistic approach to structural design. So we're actually starting to think in our code and our building design, are these structures going to be durable, sustainable, and resilient? And we're starting to see that in US practice, but we're really a long ways away from that. The other problem that we have, and I know this is predominantly a bridge audience, but the IEBC, the International Existing Building Code, which is our building code for existing structures, really doesn't establish an effective standard of care for the evaluation or design of actual repair structures. It doesn't really define the level of durability that's required or provide a really good definition of damaged structures. And that impacts how we design repairs. So really today, I'm going to talk about some new codes which came out from ACI and reports. ACI 562 was actually the concrete repair code that ACI developed. I was the chair of the second version of that code. And it's really the first document developed exclusively to provide a code for repair of existing structures. And the other two are newer. ACI ITG 11-24, kind of a weird name, but that's a report. And what I really wanted to talk about, and it is very new, it's the first document that's been published. It really talks about using statistical techniques for assessment of existing structures. And why is that important? It really is important because when we start thinking about existing structures, we can't sample everything. We can't turn a structure into Swiss cheese. But we need to understand when we do take samples, what those samples mean, and really how we can use those to better evaluate the safety of an existing structure. And what I thought was cool about this was it's kind of for those of us that took a graduate level course in reliability, it's kind of the first document that really just takes all that reliability theory that we learned, and you learned some of it in advanced statistics as an undergraduate, but puts it into one document where it's exclusively for concrete structures. So I think I'm going to talk a little bit about that today. And then ACI 440.13, which is repair design using FRP materials. And what that did was it codified a previous guide to FRP repair, and we adopted that by reference into ACI 562. So we're really trying to advance the industry that way. So the repair code, minimum performance of repaired structures. How does it do this? It's a standard. It's not a guide. Wanted to provide some clear requirements for strengthening of existing structures when it's required, and that's based upon the damage that's present. And then finally, getting into this concept of more sustainable, more durable repaired structures. So we're trying to get consistent performance and a little bit better levels of actual reliability. All these levels of performance were based upon demand to capacity ratios. And this was really based upon some reliability work that we did to establish when structures actually become unsafe and when we need to strengthen structures to current code requirements. And you can see some of these trigger values in the attached slot on the screen. But I wanted to go through how we actually use it on a typical project. And whenever I get a phone call or email about a new project, my initial thoughts are, what are we going to do? Do we need to do just a detailed evaluation? Do I know anything about the structure, or can I just kind of go out there? And then what sort of unsafe conditions may be present? And this is a project I worked on a couple of years back. And this is a loading dock / entrance to the parking garage, which you can see at the roll down door here. It's not a super heavily loaded. We're not getting semis into this thing, but fairly reasonable sized trucks are going into this loading dock. Certainly get greater than a passenger car, but not quite a semi. And what was the problem? Underneath, this is directly underneath here, this location. One-way concrete joists were basically failed and shear. And once I saw this, we started thinking, what's going on? What sort of unsafe conditions are present? But also, when we started thinking about the repair code, how are unsafe conditions defined? And a definition is presented in the IEBC. It talks about partially collapsed structures. So loose materials, yes. Example on the right, which is from Franklin Field before the repairs, that loose material held up on the netting, that's unsafe. IEBC talks specifically about a risk of collapse under service load, but what level of risk? That's not defined. That was always left for the engineer to figure out. The IPMC, International Property Maintenance Code, are to specify, is the strength exceeded by the nominal load? So is that a question? That's a little bit actually better definition. But the important thing, though, is the IEBC, the IPMC, they don't give you any information about how to actually calculate the capacity. And that's a lot of what we did with ACI 562. So when I look at this picture of this joist, is that truly unsafe? Maybe. So going back through on this project, we found that potentially dangerous conditions were present, and that's used as a trigger to require additional evaluation. And it was also used as a trigger to document the need for shoring. So what are we looking at? What are we looking at? Why is it unsafe? So the shear capacity of a joist, demand to capacity ratio, if it's greater than 1.5, it's considered unsafe. So pretty simple. Shear capacity is VC plus VS. So it's 0.5 times VC plus VS. So VC, because of the crack, is 0. When we did some radar, we basically found it's missing most of the stirrups that we're supposed to have. So 0 plus 0 of missing stirrups is significantly unsafe. So that was potentially dangerous, and we did need to shore it. How do we shore it? Owner told us very explicitly when we shored it, we needed to keep the structure open. So we provided some layout plans for the shoring. Contractor did design the actual shoring based upon the shoring load requirements and shoring placement requirements that we gave them. And we allowed that structure to remain in service once it was shored. So thinking about how we used ACI 562 on this and what were some of the advantages. The damage, the evaluation of the damage was simpler because of clear definition. As the damage was defined, we had some fairly clear evaluation requirements. The unsafe conditions, instead of being definitions, instead of being a little bit vague, were based upon damage and actual presence of conditions. And then when we eventually got into the repair design, the actual repair design was well delineated requirements. We're talking about durability. And just for background information, we ended up replacing the entire loading dock area during a winter break. It was done in 3.5 weeks, starting the day after Christmas, finished before classes started. And then eventually a coating was placed on it. And I'm going to come back to another example using ACI 562 later in the presentation, but if people are interested in the document, one of the other documents that's useful, we created a guide to the code, which is equivalent to like the old PCA notes for ACI 318. And this was jointly published with the International Concrete Repair Institute, and it provides a lot of worked examples using ACI 562 and a discussion of how the code's intended to work. So that's another useful document. So statistical techniques for assessment of, man, that's a long title, assessment of existing concrete structure. When we developed the 2019 version of ACI 562, we recognized that design professionals needed more guidance. We didn't have sufficient technical guidance on some of the statistical techniques that we're using to evaluate these structures. So starting back, when we talk about assessment of existing concrete structures, we're typically taking cores. We may be doing measurements of cover depth. We may be doing measurements of chloride content. We may get samples of material, samples of concrete from a slab versus a beam. Are those differences, and are any differences in the results? Are they statistically significant? If we have cover measurements, what's our confidence level that we have in them? So this document was put together as a way to explain a lot of those functions and a lot of those statistical functions, largely based upon Excel. So it's all built into Excel, and it helps us understand when we're doing this work, how many samples may be needed depending upon the confidence level that we want. How does the variation affect the mean value? So what are our applications, cover measurements, concrete strength? There's a lot of them. So just as a quick example of what's in there, taking a look, we have data sets shown in the upper right, 2 different sets of core strengths. There's a slight difference in the average of the wall versus the slab core strengths, slightly higher, with a slight difference in the standard deviations. Are these differences statistically significant? So there's an actual procedure outlined in the ITG where we're evaluating using what's statistically termed the F test, which is a comparison of variance. And if your F test results are greater than 0.05, it's not significant. So just for this data set, despite the differences in the standard deviation, that F test result indicated that the test results the differences were not statistically significant. And what that allows you to do, that provides you a much bigger sample of, now instead of having 12 cores in 2 different sets of samples, you can really consider that one statistical sample. And there's similar data sets. That helps you out in your analysis. Now you have a much bigger sample. Some of the other topics that are covered, if you want to have a desire, based upon a desired confidence level, how big a sample size do you need? Reliability-based assessment of member strength. So if we have a member that has a variation in maybe concrete material properties, reinforcing steel depth. How does that variation affect the actual strength of the member, and what does that mean? And the other thing that ties into, there's something called the mean load method, which allows us to do a calculation of reliability. We're all familiar with the concept of beta being a measure of how the beta as a measure of the probability of failure of a structure. We can calculate beta based upon average strength values obtained from the structure without load or strength factors based upon a first order reliability assessment. And there's a nice worked example on how you do that, which basically it's a simple way to calculate the probability of failure of a structure. So that's some of the things that are present in the ITG. And I just want to include that as part of this talk, just to make people aware that the document's available. So let's talk a little bit now and jumping guns about strengthening structures with FRP systems. There's tons of FRP type systems out there. Basically high strength fibers. These are applied to concrete structures, masonry structures, bridges, parking structures. But we're either typically using glass or carbon fibers, and then we're using epoxy to bind them to a structure. These are all high strength, lightweight. But what's the limitation? There's really been two. They don't perform well at elevated temperatures. So if you're exposed to fire, that's a problem, and they really can't, it's very difficult to fire protect these. But the other issue has really been a lack of standards and code adoption, and that's really what's changed in the last couple of years, and that's what we're going to talk about today. So different applications. Again, some of these slides are from my colleague Gustavo Tumilan at SGH. These can be used to strengthen a flexural member, where we're actually basically adding external reinforcement that's bonded. Very commonly used to increase the shear strength of a member. And you can actually, and this is not the best use of the material, you can provide some axial strengthening. But more importantly, with these, when you wrap them around a structure, you're providing better confinement. So you're increasing the confinement, which allows for better seismic performance. So those are some of the common applications. And these can be internal or external. The previous slide, they were all on the exterior, and they're using the epoxy to bond to the structure. When you're doing it internally, you're cutting a slot in the structure, and then you're using epoxy or other adhesive to bond the structure, to bond the FRP bar back into the concrete structure. So some design considerations. What's really being done? ACI 562, we adopted the ACI 440S document by reference, and what ACI 440S was really a codified version of the ACI 440.2 guide. So in terms of hierarchy, a guide cannot be adopted into a code. Only a code can be adopted into a code. When you adopt a code by reference, that brings all those mandatory requirements of the specialty code, in this case 440S, into the adopting code, which is 562. So what this does is this allows us as an ACI 562 member to get all the strengths and all the critical knowledge that's in the ACI 440 brought in, and it's a lot simpler process, so we don't have to repeat it in the actual ACI 562 codes. This is the process that was put forth, and this new code now allows direct use of FRP in a design code. Couple things. One primary limitation when we're talking about FRP structures. When we're adding in an FRP structure, we have to have some minimum capacity without the FRP being present. And that's shown in those two load combinations there. And why is this necessary? We think about an FRP as basically an external reinforcement that's added onto a structure. That FRP can be damaged by impact. It can be damaged by idiots with grinders. It can be damaged by miscellaneous tradesmen that don't understand what it is. So there is a possibility, may not be high, that an FRP can be cut or made useless during service. So we have these minimum capacity. And what this minimum capacity also does is provides a backdoor limitation on how much FRP can be added to a structure. What does that mean? When we're thinking about reinforcing something, we're trying to take it up to like 1.6 live load, 1.6 live load. And our minimum is 0.5 live load. The maximum really that we're adding in terms of strengthening is about 1.1 times the live load. So that's kind of providing a limit as to how much FRP. Why is that important? Because when you put on too much FRP, it just doesn't work. You can't get the strain into it, and it doesn't work. So this is another way of limiting how much additional reinforcement can be added to a structure. And this further prevents brittle failures of reinforced concrete structure. The other considerations during a fire event, you need to have a minimum strength of the structure, and that's similar. But when we're doing this, we're considering the properties of the concrete structure during the fire event, as well as the internal restraint that's provided by the structure. So there are some limitations in terms of load combinations when we are using FRP, but not going to go through a case study, not a super detailed case study, but taking a look, we have an existing two-way slab, 6-inch slab. You can see some drop panels that are present. Those are 2-inch thick drop panels. And there's an interest in having a superimposed dead load of 10 PSF, a live load of 40 PSF. And there's a question about the capacity of the slab. To evaluate the structure, what was done, cores were done for doing concrete compressive strength samples as well as slab thickness. And then GPR was used for locating existing reinforcing steel. And in terms of this presentation, both of those topics could be full 1-hour seminars just on those two topics alone. So different loading scenarios that we had for this structure. Live load, superimposed dead. We ended up with different combinations of dead load and live load. And when we started looking at some of the results, we found that the demand, MU, was greater than the existing capacity based upon where the reinforcing steel was. Not horribly deficient, if you take a look, thinking about depending upon the location, 10% deficient, 10%, 20% deficient. Not horribly deficient, but still deficient. So a decision was made that some sort of strengthening would be required. So what are the options that you have? You could try and cut in and add more existing bonded reinforcing steel. You could try and increase the surface depth, but that adds dead load. So the FRP in this situation was really a nice choice because it's lightweight. It adds almost no load to the structure. Fairly well-defined design procedures. And really, what are we doing? We're upgrading the section. So in terms of concrete, it's the existing capacity from the reinforcing steel plus the area of the fiber, the width of the fiber. So basically how much FRP we're adding, the effective stress that we're allowing on the fiber times the depth of the section. It's conceptually exactly the same as you're doing a conventional reinforced concrete design conceptually. This example doing FRP sheets, so finite sheets, and what we're doing with those sheets, we're thinking about both the rupture strain and the tensile strength of the fibers, and then figuring out what the effective strain would be when we're actually applying them to the structure. So we're actually reducing down the nominal design strength to create an effective strength, considering the environmental exposure, and the effective strain prior to failure. So what does that look like? Taking a look at different sections, a single ply of the fiber, 30-inch spacing, 12-inch wide strip, adding that onto the existing reinforcing steel on the top side, and we end up with a calculated minimum strength. We check our minimum strength, that was okay. And then at the interior supports, we're adding in one strip with the FRP, space 30 inches on center. And then we're determining that the upgraded strength is substantially better than originally designed strength. We could actually probably get rid of some of that FRP, make that a little bit thinner. Again, looking to confirm that the minimum strength was satisfied. Again, it's one strip of FRP on the bottom side, now 60 inches on center. So some simple calculations, what the midspan looking at. And then, so what does it end up looking like? Depending upon where you are, this is bottom surface, top surface, different amounts of FRP that are bonded in to allow for strengthening of the one-way plate, where most of our strengthening is actually added in our negative moment regions near the columns. But what's our advantages of this? This is a minimal weight solution. There's almost no added weight. This is added in with minimal disruption. We're basically grinding this. We're grinding, cleaning the concrete surface, allowing it to be installed with minimal disruption to the owner, and it's relatively quick. So going back to ACI 562 and really trying to improve that concept of durability now, addressed in Chapter 8 of ACI 562, when we talk about durability of a structure, it's a we problem because there's a whole bunch of people. The code itself recognizes that an owner may only want to own a structure for 2 years, so they may not be interested in long-term durability. And we also have the problem where we're talking about the durability of repairs, the repaired structure, and how that repair and the repaired structure interact. We recognize the need for maintenance, and then we sort of have some ghosts. Ghost of Christmas past, what do we start with? What do we want to achieve? That's the ghost of Christmas present. And the ghost of Christmas future, what's going to happen in the future? Is the design professional going to design for durability? Will the owner maintain it? Will a contractor provide us a decent starting point? These are sort of all the questions that we have when we start talking about durability. And talk about durability, just as a quick case study from my past. This is a parking garage repair. It's in Stamford, Connecticut. Post-tension beams and slabs. And in 1994, about 30 years ago now, there was a substantial repair program completed. I was involved with the repair design, and 260,000 square foot, 900 car garage. Fairly extensive repair was done. A lot of strengthening was added. You can see the large beam that we added. And basically at the end of the repair project, the owner said, "You're the nice guy, Keith." My boss at the time, Randy, "You're a nice guy, but I don't want you guys back in here forever. I don't want to see you guys. We need a long-term protection plan for the slabs. We need a coating. And I don't want to see you guys for at least 15 years. As a design professional, we recognized that this was a parking structure exposed to chlorides, needed traction, and we needed long-term performance. So we looked at a whole bunch of different options. And you can see me 25 years ago out with our owner looking at the performance of actually bridge deck overlays, multi-layer epoxy overlays. But why do I bring this up? A lot of what we were thinking about was brought into the ACI 562 code. So with some code specifics, thinking about cause occurring conditions, making sure that our repair materials are compatible with the structure and the service environment, talking about considering moisture transmission through the slab. We're talking about adding an epoxy, which is a moisture barrier. So that needs to be considered. Interaction, impact of abrasion, cracking, and then establish construction inspection requirements so that we're actually getting what we want. As I said, we eventually decided upon applying a multi-layer epoxy overlay. It's bridge deck technology. We did a trial installation. We did a lot of pull bonds. We did a lot of pull bond testing during construction when we did some more chloride permeability to make sure it was working. These are some of the initial on the right. You can see some of our initial test results that we had, and it was consistent. The graph, some of you may recognize the graph. It's from the SHRP program, the original one, not the one that was done, not Sharp 2, the original one, where they looked at different performance options for bridge decks. And this is actually a lucky project for me. This is some of our construction pictures. We flooded the cracks with the epoxy. We took some restraint. We added in some saw cuts, did a lot of calculations, make sure our thermal compatibility was working. But the project, as I mentioned, was actually completed in 1994, probably before some of the people in the audience were born. It's kind of scary. But I've been lucky on that project in that I've been able to go back to that structure and look at how it's actually performing. And 2019, and actually did one a little bit later than that, but we're talking about 25 plus years now after installation, we're still seeing good bond performance of the structure. We're still getting, as you can see in the graph on the right, we're still getting good tensile rupture strength. Very little overlay delamination, no chloride ingress. One of the problems we had is our expansion joints failed basically as soon as the warranty ended. But what this is really telling us is that if we think about durability and repairs, we can actually get there. So we started this presentation talking about all the problems with repaired concrete structures and a lack of durability of concrete structures. But I think what we're actually doing now with some of the ACI, new ACI documents, we can improve the performance of concrete structures. We can do this in a very specific way. We need to create standards. There's establishing minimum requirements for repair. We need to actually get design professionals thinking about how we're going to assess these structures so that we're not missing existing conditions. We're actually we're getting people thinking about structural reliability and long-term durability as part of our repair design. And then at the same time, we need to think about the owner's goals and requirements when we start talking about long-term durability, because it did cost more to do that project that way. And it does. And now if I want to mitigate future damage, it will cost more. And that is a cost that the owner is going to have to bear. And we have to recognize that may not be an owner cost that the owner wants to repair. So encouraging and thinking about with our owners how we're going to assess these structures and understanding what their goals are. The other thing we're doing is we're bringing in new materials and new techniques and making them more available. So the FRP materials, these have been around for 20 plus years, and we're really getting to the point where we have them in the code. People can use them now. They're readily available. We should be teaching students about how we can use them in as undergraduate students or in grad school. And then really as design professionals, learning how we can use some of these statistical techniques that are in the ACI ITG as to how we can better assess the expected performance of repairs and what the expected reliability of structures are. And I guess with that, I'm going to open it up to any questions. But before I do that, there are a couple people I'd like to acknowledge, the committee members that really put in a lot of effort on all these documents. And Kevin Conroy, the colleague of mine, Tarek Al-Qadaji with Structural, and Khalid Nalawi with ACI that provided a lot of the background slides. So I guess with that, I'll just kind of open it up to see if anybody has any questions.
So I don't see any in the Q&A, but I did have a question. Is
Sure.
there a way to coat or protect the externally bonded FRP to reduce the impacts of the extreme heat?
I mean, there's not a good one. You do see some people are putting cementitious coatings on top of the FRP. And the problem is if you have something externally bonded and exposed to fire, it just doesn't hold up. There are some epoxies that have better thermal performance, but it's not common. And really, once you get to a temperature of about, depending upon the epoxy, it's 180 or so degrees Fahrenheit, you start to see softening of the epoxy material, and you get into the glass transition temperature of the epoxy, which is when it starts to actually degrade. And then carbon burns. I mean, obviously we've been burning carbon for millennia, so carbon burns. Glass will behave a little bit better at elevated temperatures, but it's the question about the adhesive. You can protect them, but I just don't think it's that effective.
Gotcha.
And that's also a problem. I didn't talk about it in this presentation. ACI has also created a specific code for design of structures to be reinforced with glass fiber reinforced bars. And that's been being adopted into the 2024 IBC. The limitation on those is it's really structures that don't have a significant fire rating. So those are the limitations of the materials.
Thank you.
Other questions?
I don't see any. And I'm now sharing the certificate for attendance. I'm also putting a link in the chat so you can download the file. Keith, I want to thank you for a great presentation. I've learned a lot, and obviously codes do kind of drive a lot of what we do in our profession. Though as a geotechnical engineer, I tend to dabble in the blackest of engineering black magic. But yeah, this is great. ACI, right? My experience with ACI has always been how to test concrete in the field to make sure they're doing it right.
Well, and that's really, where does durability start? And that's really where durability does start. And I'm going to throw in one last plug. In 2 weeks, ACI is having our annual convention. It's actually in Philadelphia at the Marriott. If anybody's interested, unfortunately, it's not free and it's not cheap to register. But if anybody's interested, you can go to concrete.org, or if you want to come by and sneak in, I'd encourage that as well.
All right. Well, if there's no further questions, I bid you adieu. And remember, we have events coming up mid-November. It'll be another virtual event, so look forward to people registering for that. And join us on LinkedIn. We're excited to get people involved. And Keith, thanks again for a great presentation.
Thanks for having me. I appreciate it.
And a happy Halloween.